You're listening to the Good Question Podcast with Richard Jacobs. Our goal is to make each of our guests exclaim, that's a good question. I don't know the answer. Because when that happens, it means you, the listener, may be inspired to learn more beyond the interview and to ask great questions yourself that lead to new insights. In this podcast, we cover historical and current anthropology, comparative religion, and history. Welcome, and let's get started.
Hello, this is Richard Jacobs with the Good Question Podcast. My guest today is Jeff Auletta, MD. He's a Senior Vice President, Health Equity at NMDP and Chief Scientific Director at another act, CIBMTR, which we'll explain shortly. Jeff, just for a quick start, you want to explain both acronyms to this, make sense?
Yeah, no problem, Rich. So thanks for having me on. As is the case in medicine, there's always a bunch of acronyms. So NMDP was formerly known as the National Marrow Donor Program, but is currently known just as NMDP. And that organization is a global nonprofit leader in cell therapy, and it helps patients who battle blood cancers and disorders in order to find a cure and to save their life. So that organization is basically one that helps to procure cells that make our circulating blood cells. So that's NMDP. CIBMTR is the Center for International Blood and Marrow Transplant Research. It is a research collaborative between NMDP and the Medical College of Wisconsin, and it looks to transform patient outcomes through research, both through a massive database of information as well as prospective clinical trials.
So these are for blood type cancers primarily, like instead of solid tumor cancers? Okay, so like leukemia, blood cancer itself. I'm not sure some of the other major ones that you would see, but what are they?
Sure. So the big ones are acute leukemia. So there's acute lymphoblastic leukemia, or ALL, and acute myeloid leukemia, or AML. And leukemia gets its name by the types of cells that you see under the microscope. So there's lymphoblasts, so ALL, and there's myeloid cells, or AML. And there's also another disease called myelodysplastic syndrome, where the bone marrow, which is the manufacturing site of the blood-forming cells, has an abnormality associated with it in terms of the cells as well as the environment of the bone marrow itself. So those are the three top disease indications for an allogeneic stem cell transplant. In other words, when you get someone else's blood-forming stem cells, that's allogeneic stem cell transplant.
Okay, so what is the role of the bone marrow versus the blood itself? I had thought that the marrow is where, I guess all the red and white cells are produced.
Yeah, that's exactly right, Rich. So you can kind of think of the bone marrow itself. So when you touch your arm, there's the hard bone that's called the cortex. On the inside of the hard bone is a spongy layer called the bone marrow. And that bone marrow is literally like a bird's nest. So there's lots of different cells that are involved or inside the bone marrow. And the blood-forming or hematopoietic stem cell, that's like the egg inside the nest. And so that hematopoietic stem cell divides into itself. That's why it's called a stem cell, but it also differentiates or becomes the circulating blood cells, like the white blood cells, which fight infection, red blood cells, which carry oxygen throughout our bodies, and platelets, which help us to stop bleeding. So this master cell, this master hematopoietic or blood-forming stem cell, is what we collect at the NMDP from patients in order to provide as a stem cell graft to transplant patients who have hematologic cancers like the leukemia, as I mentioned, lymphomas, and myelodysplastic syndrome.
Can you only take them from the bone marrow, or can you take them from the circulating blood?
Yeah, great question. So you can there are three sources of hematopoietic stem cells. One is the bone marrow itself, because that's where these cells live. The other is peripheral blood, and we'll talk about that in a second. And the third is from the umbilical cord. So when a woman gives birth to a child, obviously the fetus comes out, it's a living human being, but the placenta then comes out, and the physician can access the umbilical cord, the vein there, and withdraw blood, and that's a stem cell source. That's umbilical cord blood. Bone marrow, we do bone marrow harvests where donors are usually put to sleep, and we access their hip bone and literally pop through that cortex part I call the hard part, and you actually end up with the needle and the sponge. You withdraw draw and you do several collections from bone marrow stem cells. And the third is the peripheral blood, as you mentioned. So again, I talked about the hematopoietic blood stem cell as being the egg in the bone marrow. You can also kind of think about it as a ship or a boat rather at the dock. So the reason why the boat stays at the dock is because it has ropes that are tethered to the dock. So we have certain medicines called growth factors that literally could clip the ropes so that the stem cell or boat kind of drifts into the bay and ultimately into the river. So that's the analogy of the stem cell. It's called stem cell mobilization. So we use the cytokine to take that egg and to basically have it enter into the bloodstream. And that's what we call stem cell mobilization. So that's how we get peripheral blood stem cells, is that process.
So you cause the bone marrow to release some of these hematopoietic cells, stem cells into the blood itself.
That's correct. Yep. So we literally can kind of goose what happens naturally. So we normally, all of us have these hematopoietic stem cells because if we didn't, we wouldn't survive because of our circulating blood cells have a finite longevity to them. And usually, for example, the white blood cells tend to be the ones with the shortest lifespan and versus the red cells and platelets. So if we didn't have this master hematopoietic blood cell to replenish our circulating cells, we obviously wouldn't live. So that's where we can actually, naturally, we have this occurring in our bone marrow all the time. What we can do is augment that response. So to make more of these hematopoietic stem cells leave the bone marrow by using that cytokine mobilization that I mentioned.
Okay, so when you do this, do you have to tune the response? Too much of it, and I guess you'd exhaust and deplete the bone marrow, and probably bad things would happen. Too little, it's not useful. How do you do that?
Yeah, great. It's a great question. So, we were made in a very nice way as human beings. In other words, the reason why, again, these are called stem cells is because they make themselves. So there is a limitless, non-limited supply of these hematopoietic stem cells because they're constantly making themselves. So you can, in fact, enter this world where giving some people are what we call super mobilizers, where they have a very high response to the cytokine, so that they have lots of stem cells. And these tend to be actually younger kids tend to mobilize stem cells more than adult patients do. And so oftentimes you can get into very high white blood cell counts because the cytokine, again, stimulates the cell to divide into white blood cells. So in that regard, Rich, you can kind of overdo the system by producing a higher white count. And there's a collection called an apheresis. It's a machine that looks like a dialysis machine where literally their blood is being extracted from the body, goes through this machine, spins, separates out the white blood cell layer, which has the hematopoietic stem cell, and returns the rest of the blood into the donor's body. So that's how we literally are collecting the hematopoietic stem cells, is through that apheresis process. So if you have too much of a high white count, then that throws off the process. But ultimately, things work out, and we're usually successful in terms of getting a good yield of these hematopoietic stem cells.
Yeah, but okay, can they make white and red cells or only red? I mean, only white.
They make all three. They make the white blood cells, which fight infection, the red blood cells, which carry oxygen, the platelets, which help us to stop bleeding.
What do their behavior is governed by what? What's in the blood? If you have high white cell count, they'll tend to make more red, or what will they do?
It's a great question. And again, it goes back to how we were created. So there is this regulation that occurs that you're alluding to, Rich. It's just like our gas tank, right? The indicator light goes low, so we know we have to get gas in order for the car to get to keep on going. Same thing with the bone marrow. It basically senses, which you're alluding to, if there's a low amount of red blood cells, patients who are anemic or bleeding, those hematopoietic stem cells kind of kick in and make more red blood cells than white cells or platelets. And those cytokines that I mentioned, the one that we use is something called GCSF. The G stands for granulocyte white blood cells, so that's why the white blood cells increase in the system. But there are other cytokines that are specific to literally kind of tapping the hematopoietic stem cell and saying, hey, I want you to make a red blood cell instead of a white blood cell, or a platelet instead of a red blood cell. So again, we're we were created in such to have these chemicals in our bloodstream to help regulate what the hematopoietic stem cell divides into.
But do you dope the surrounding blood, let's say with the right kind of cytokines, or maybe you draw blood from them earlier and then put back only the red cell component to create a high red cell environment, to preferentially make white if they have high white cell count to begin with. Like, what can you do to kind of game or coax the hematopoietic cells once they're liberated to make what you want?
Yeah. So now we're kind of getting into a really great field called cell therapy. But in order to kind of continue with this, we can, in fact, what are called leukapheresis patients. In other words, take off only their white blood cells, again, through that process of apheresis that I mentioned. We can, in fact, remove red blood cells through that process as well, or we can actually just, literally kind of drain those red blood cells if we needed to. And then usually we can't necessarily take off, we can take platelets as well. So in other words, the American Red Cross, great society, right? We all should go to the American Red Cross and donate blood. The American Red Cross can take whole blood from us. In other words, you sit in a chair, you give them your blood, and it goes into this big bag. Whole blood contains everything. That's the name whole blood. You can also give plasma, which contains the antibody layer and also some other chemicals, and you can actually be apheresed in order to get platelets as well. So you can, in fact, manipulate the blood and collect certain components of it based upon the techniques that I just mentioned. But for our purposes of hematopoietic stem cell transplant, we give the cytokine. It gooses or augments what naturally occurs in terms of the stem cell being emigrated out of the bone marrow into the bloodstream, and then we collect the stem cell through that apheresis procedure.
Okay. Are you able to, what do they call it? You start out with a few cells and you culture them into the millions and billions. Are white cells culturable or red cells culturable, or they have to be made de novo, from source material, can be mass produced or created in big amounts?
So this is a great question. So there's a whole field looking at ways to make artificial red blood cells. And there's lots of different ways to do it. But the whole point is, as you can imagine, our war fighters, they go into battle and they get shot, for example, or exposed to a bomb. And so you have to give emergency transfusion. So there's a whole field looking at ways of, using this ex vivo or outside the body production of red blood cells. So as I mentioned, American Red Cross obviously uses live donors in order to get whole blood and plasmapheresis and also ways to collect antibody through apheresis as well. But there's a whole field of regenerative medicine, which is looking at ways to be able to do this outside the body, and red blood cells are one of them. The other thing is, though, there's a whole field that's looking at ways to manipulate cells outside the body called cell therapy. So we are involved in cell therapy as bone marrow transplant physicians, and we can take certain cells out of the body, educate them outside the body to do certain things, either attack cancer inside the body or attack viruses inside the body as well. So that's a whole field that's really blossomed in the last 20 years.
What about looking at the cell-to-cell signaling in blood? Has anyone done that to look for like exosome production, from white to red, from red to white? What's the other analysis?
Yeah. So once kind of that lineage that I mentioned, so you have this master hematopoietic stem cell, it differentiates into these progenitor cells, which then differentiate into more committed cells. So what you're alluding to is kind of the ability to go across lineage, right? To go from white blood cells to red cells to platelets. And the only cell that can do that is the hematopoietic stem cell. The progenitor cells, in other words, myeloid progenitor, lymphoid, is the first separation into that tree. They can actually make different types of cells, but the further along you go, the more differentiated as a cell you become, and the less likely you can, become something else. Having said that, there's the field of looking at pluripotent stem cells or inducible pluripotent stem cells, iPSCs, which is incredible because you can actually take a skin cell, for example, and potentially change its lineage outside the body for it to become another type of cell. But that's, again, something outside of hematopoietic stem cell transplant.
What about the platelets? What role do they play? Are they created, by the bone marrow, or are they created somewhere else? And how do they relate to the concentrations and availability of white and red cells?
Yeah, so they too derive from the hematopoietic stem cell. So they have a certain chemical called thrombopoietin. That's that cytokine that I mentioned that stimulates or taps the hematopoietic stem cell on the shoulder and tells it to become a platelet. So thrombopoietin is that type of cytokine. Erythropoietin is the cytokine that stimulates the stem cell to become red blood cells. And then the GCSF that I mentioned in the stimulates the stem cell to become white blood cells.
Okay. But what role do the platelets seem to play or even the cytokines themselves? I mean, if there's a large amount of cytokine of one kind, does that suppress the production of other cytokines, or do the cytokines do signaling that, again, outshouts the other signaling from other cytokines? Like, who has played with the dynamic of all the constituent parts of the blood to make it do X, Y, or Z?
Yeah, so that's a great question. There are lots of different chemicals floating around in our bloodstream. And the reason why we survive is because we have this fight and flight mechanism, right? So it's sympathetic and parasympathetic nervous system and discharge. The same thing in terms of the way our body responds to challenge, environmental challenges. So for example, infection. So when we get a cold virus, that's stimulating our immune cells in order for them to do a couple things. One is to produce some of these cytokines, which stimulate other cells to come along. So that's called recruitment, to attack the virus. It also kind of stimulates the progenitor cells to make more of these cells. So that's production. So you have recruitment and production. And then you have elimination of the virus, because some of these chemicals can actually directly target the virus as well. So at any given time, we kind of maintain this state of homeostasis. In other words, we have everybody ready to the call to action should there be kind of an invasion of our bloodstream through a virus. But we also don't want to overreact, right? Because if we constantly had reaction going on, then we would actually start to attack ourselves. And some people actually have that problem. It's called autoimmune disease. So that the immune cells are attacking certain parts of their body, like, for example, Crohn's disease or inflammatory bowel disease. Those patients don't have cells to quiet the immune cells, and it causes an autoreactive loop to occur, and so they have inflammatory bowel disease from it. So back to your question, is there are many chemicals floating around our bloodstream that tell the body, at least the progenitor cells and the hematopoietic stem cells, to either kick in because we need your help. There's like infection here, so you got to become another cell real quick, or we need you to quiet down because we can take care of things and we don't want it to become a riot in the bloodstream. So you kind of have these police cells to maintain order in the body so that you don't get autoimmune disease, for example.
What happens in a bloodborne cancer like a leukemia? The two types, there's the ALL and the AML.
Yeah, so the reason why people get cancer in general, and particularly with regards to the leukemias, is really whittling it down to two things. The first is the analogy of basically no regulation. So I mentioned regulation in terms of like autoimmune disease. So there's regulation in terms of cell growth, right? Because if our cells continue to grow and divide, then you get cancer. So that's one hallmark of cancer. It's like a car that blows through the intersection, doesn't adhere to a stop sign or a red light, and keeps on going through. So same thing, cancer doesn't adhere to a stop sign signal and keeps on growing. So that's one hallmark. The other thing is it fakes out our immune system. Again, we have these kind of police cells that go around through the body and check out and make sure everybody's doing the right thing. And if they see that there are people or cells rather that aren't doing the right thing, they get rid of them. So our immune system recognizes ourself and then eliminates non-self. That's, what's not ourselves. So cancer basically blows through the stop sign, doesn't check stop growth, but it also fakes out the immune system so that those police cells can't recognize it as cancer and eliminate it. So that's the whole point of allogeneic hematopoietic stem cell transplant for a leukemic patient, is we're replacing the immune system of the patient because their cells have been faked out by the cancer. So we're infusing another immune system into the patient so that those hematopoietic stem cells find their way back to the bone marrow of that patient, produce other circulating cells, produce those kind of police cells that then recognize the cancer as different and eliminate it. So that's something we call graft versus leukemia effect. So the graft are the donor hematopoietic stem cells infused into the patient. They become the attacker cells that eliminate the leukemia in the patient. So that's exactly why we give an allogeneic stem cell transplant.
Is it the hematopoietic cells themselves that become cancerous, or is it the white cells, or what is it that actually, again, becomes cancerous?
Yeah. So it's usually what happens is, again, that analogy of the car, normally when we approach an intersection, we put the brake on, right, lightly, and then ultimately come to a stop. So as I mentioned before, the hematopoietic stem cell divides into progenitor cells, which then subdivide into the differentiated cells, white cells, red cells, platelets. We know that leukemia actually causes an inability to stop differentiating and promoting an earlier cell form. So it's almost as if the progenitor cell doesn't differentiate into the red cell, platelet or white cell, but stays at that earlier developmental stage and becomes leukemia. So that's
like a third path, or is it just like a monstrous abomination of what it would have normally become? What does a third path look like? Is it completely destructive? Does it have certain abilities?
Yeah, great question. So that's the field of leukemia genesis. So leukemia and then genesis, promotion of leukemia. So lots of people are studying this, and what they found are a couple things. Number one is that there's abnormal signaling inside the cell. So in other words, remember I said that the tap on the shoulder for the hematopoietic stem cell? So there are certain taps on the shoulder of cells that activate the cell to do something. And the reason why cells can become activated is because they have what are called receptors on their surface. And so those receptors basically recognize certain chemicals. And once that docking occurs of the chemical with the receptor, it then stimulates signaling inside the cell. And that signaling then ultimately causes the cell to produce something like protein, for example. So leukemia genesis can happen because there's abnormal sensing at the surface, abnormal signaling that's activating the cell, and abnormal promotion or growth of the cell. So there's lots of different ways of leukemia genesis to be formed.
Okay. So what is your angle of attack here? It's again, your specialty is just being able to generate with good quality and good quantity and release these hematopoietic stem cells to fix the blood?
Yes, not necessarily. So allogeneic stem cell transplant. So again, we're taking these stem cells from another person and fusing them into a body that's different. So those stem cells, again, are going to recognize things that are different from themselves. So what I mean by that is it promotes, hopefully, that graft versus leukemia effect. But on the flip side of that alternative immune system can actually cause damage of the patient's tissues, something called graft versus host disease. In other words, the graft is attacking the host, the patient's tissues. So you can get symptoms like very bad skin rash or irritation, profuse diarrhea, and liver enzyme elevation. And these are what are called target organs of graft versus host disease. So we have to promote what's called tolerance in the body. So what happens is when a patient gets a stem cell transplant, they're actually getting a preventative medicine to decrease the chances of graft versus host disease. And there's lots of different medicines that we use in order to do that, but they all pretty much have the same effect, which is kind of quieting the T cells, the donor T cells, which are the specific cells that cause the tissue damage in the patient's body. So it's not simply infusing stem cells and you're cured. It's infusing stem cells and taking care of the complications associated by the abnormal immune response. But in addition to that, patients have to be prepared for transplant. And what I mean is their body has to be prepared in the sense of getting combination of chemotherapy or radiation, something called the preparative regimen, in order to suppress their immune system so they don't reject the graft, but also to eliminate any residual cancer clone. And this is some really high-powered stuff. In other words, if I were to give you the same amount of chemotherapy and radiation, your body, depending upon the intensity of it, would actually need stem cells because I would have ablated your bone marrow in terms of the intensity. That's called myeloablative conditioning. So again, that has side effects associated with it in terms of skin damage inside the mouth, as well as organ dysfunction of kidneys. So in the field of stem cell transplant, we give radiation and chemotherapy, which causes acute and long-term side effect. But in addition to that, we have to treat and prevent that graft versus host disease from happening. So it's patients who receive an allo transplant are usually hospitalized for a good 4 to 6 weeks up front, and then follow up in clinic and in order to be monitored, and also are at high risk for infection because it takes a while for that immune system, number one, to kind of get used to its new environment, but number two, to be healthy enough to fight off infection.
Where is this graft occurring? Like, are you injecting into the bone marrow, or are you placing into the bone marrow, or can you just inject into the blood? Like, where does that have to go?
Yeah, it's just like basically getting intravenous fluids. In other words, we give it through the vein. So what happens, it's like a regular blood transfusion. A bag is hung, or a syringe is used to inject the stem cells into a catheter that goes through one of the major blood vessels. That's what we call a central line catheter. And so what happens is literally you inject or have the stem cells drip into the bloodstream, and they literally will circulate through the bloodstream, and they will find their way into the bone marrow. So as you can imagine, the reason why the bone marrow, we have stem cells there that make blood cells, is because it has vessels for those cells to go into. The bone marrow does. So there are vessels that go into the bone marrow. There are vessels that come out of the bone marrow. And so the hematopoietic stem cell circulates throughout the entire body. Some of them find their way into the bone marrow, and literally they're like the pilgrim. They find their way into the bone marrow, and they start to make a colony of other stem cells. And ultimately you kind of get enriched in that particular area, and these stem cells start to work and make the circulating blood cells. And so the analogy I give to patients is your bone marrow is like a 50,000 seat stadium. So it takes a while for all the 50,000 fans to kind of pile into the stadium. Same thing with this process that I'm mentioning, which is called engraftment. So it takes a while for those stem cells to fill the seats of the stadium, and then to become the circulating blood cells. So that's why patients often need blood transfusions of red blood cells and platelets until those seats are filled, and that body can then produce enough of the circulating blood cells where they don't need transfusions.
Yeah, it's weird. It has to soak into your bones, literally.
Yeah.
But you don't have to inject directly into the bone. They can be carried in there.
Exactly. So they find their way because, again, there's a whole signaling cascade that occurs in our body. So there's these certain chemicals called chemokines, and the chemokines and there are receptors on the hematopoietic stem cell, so that, again, the chemokines are literally kind of like coaxing the hematopoietic stem cell to come to me into the bone marrow. And once it does, then the hematopoietic stem cell will dock again at that area, that analogy of the boat docking there, and then will stay there and reproduce itself until it's given the tap on the shoulder to kind of make the other cells and enter the bloodstream. Okay. We were made the right way, Rich. I got to be honest with you, right?
What do you mean by that?
Oh, the master creator did a nice job.
Yeah, no, I mean, it's unbelievably complex and amazing. Yeah, definitely. So what happens now? Is this clinically available, your process, or is there still more to do to make it clinically available?
Yeah, so it is clinically available. Stem cell transplant has been around since actually 1969 was the first allo transplant that was performed. And the field has definitely improved over time. So overall survival has improved over time. But the top 3 things that patients die from a stem cell transplant are primary disease relapse. So in other words, we want that graft versus leukemia effect. However, the cancer has an edge and it gains an advantage in order to still fake out the donor immune system. So primary disease relapse is the number one cause of patient demise. The second is organ dysfunction. In other words, we're giving those high doses of chemotherapy and radiation, and those cause problems for people, particularly for people who have comorbidities, for example, diabetes going into transplant or advanced age. And so getting more of these chemicals or toxicities can cause permanent damage to organs. And the third is infection. And again, it has to do with it takes a while for the seats to be filled in the stadium and for those white blood cells, those infection-fighting cells to be made and to mature enough to function well in order to get rid of infection. So the field right now is still looking at ways to optimize outcomes after transplant. And the way that we're thinking about that is certain kind of graft versus host disease, medication, certain kinds of cellular manipulation, as I mentioned, outside the body, and then ways of making the graft kind of different in terms of its composition of cells. And again, ways to prevent graft versus host disease, prevent infection, and enhance supportive care in order to optimize outcomes.
Okay. Well, where can people keep tabs on this process and the advances coming from it? How do they best find you and your work?
Yeah. So right now at NMDP, they can go to nmdp.org or they can go to CIBMTR.org and learn about this. Here at NMDP, we are sponsoring research that has led through our CIBMTR prospective clinical trials, looking at mismatched unrelated donors. In other words, being able to use kind of a not so perfect match between the blood cells of the recipient and the blood cells of the donor. And that allows us to be able to provide this life-saving therapy to patients who particularly have a hard time finding a donor, because in the registry that we have, it's mostly comprised of non-Hispanic white patients based upon those folks who have given a swab in order to become registrants. And so therefore, the genetic profile is more skewed toward non-Hispanic whites. And so therefore, finding a match between the patient who is, for example, African-American versus a Caucasian patient is definitely higher, 80% chance for a Caucasian patient versus a 29% for finding a match for an African American. So we wanted to do something about that. And so we wanted to create an equal opportunity to find a donor for a racially, ethnically diverse patient. And so the way that we're doing that is by crossing over that barrier, that immunologic barrier of matching between the donor and the recipient by using a special kind of graft versus host disease prophylaxis called post-transplant cyclophosphamide. So that enables us to use more mismatches to provide to patients of ethnically diverse backgrounds. So now with MMUD or mismatch unrelated donor transplant, the existence of a donor increases dramatically based upon the level of mismatch for an African American patient. So remember that was probably a little bit process. Yeah. So that 29%, now we can also get it almost up to 100% by just 2 levels of mismatching.
Yeah, that's great. Well, very good. We're just about out of time. So like I said, for people to follow up, what is one place they can go to, to follow up on what they're doing with you?
Sure. NMDP.org is, again, the donor registry. And they can, if they're interested in becoming a donor, they can certainly go and check out that website. And then for the research part of things, they can go to CIBMTR.org.
Very good. Well, Jeff, thank you so much for coming on the podcast. And you're a very good explainer, very good communicator of these concepts. So I appreciate it.
Oh, thanks, Rich. And thank you for having us. And if you need me, please, happy to come again.
Okay, excellent.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
Thank you for listening to the Good Question Podcast. Please email support@thegoodquestionpodcast.com if you have any referrals to great guests for us to interview. Visit thegoodquestionpodcast.com to hear more interviews. And please help us spread the word by rating and reviewing us on Apple Podcasts, iTunes, Spotify, YouTube, or wherever you listen to this podcast.